Hi, today we're looking at the law of conservation of energy with heat. So we've already talked about law of conservation of energy earlier on in this unit. With it, however, we only looked at the conservation of kinetic and gravitational energy. And when we looked at it, we talked about how energy can neither be created or destroyed. It can only be transformed into other forms of energy. So this means our initial energy will always equal our final energy. So for example, if we have, say, an object sliding down a ramp and object started stationary, it's going to be losing gravitational potential energy as it goes down the ramp, but it's going to be gaining kinetic energy and thermal energy, and the kinetic energy and thermal energy at the end will equal how much gravitational potential energy we've lost. So this brings us to the equation. Our change in kinetic energy plus change in potential energy due to gravity plus our change in thermal energy equals 0. So the amount of overall change in energy is 0. So the energy level in our system remains constant. Now I'll talk a bit about thermal energy. We have looked at one equation for thermal energy earlier on, which dealt with heat capacities. We will not be using that formula for this case. In most cases, our energy being lost is being lost due to friction as something slides down a ramp, for example. So we have a friction force, we also have a distance, which we can then use work, which is force times distance. So our energy that is not being transformed into kinetic is getting changed into thermal energy because of friction, and that means that in that previous equation, our change in thermal energy is our force of friction times our distance. So we're just using our work equation to figure out how much energy friction is using up. We can now rewrite our original equation for our potential kinetic and thermal energies along with our actual individual equations for kinetic, gravitational potential, and thermal energy. So we have 1/2 mv squared minus v naught squared plus mg change in y plus our force of friction times our distance. And that equals 0. So we'll utilize this to do a couple examples. Our first example, we have a box sitting at a height of 20 meters on a plane that is inclined at 30 degrees, which has a horizontal distance of 34.6 meters. We're told the box has a mass of 15 kilograms and there's a coefficient of friction of 0.15. And we want to know what will the velocity of the box be when it reaches the base of incline, and we want to do it to two significant figures. So first thing I'm going to want to do is figure out what the actual length of incline is. Because the length of incline is the length that the object is rubbing against the surface, so that would be our distance where our friction is taking place. So because we have two sides of a 90-degree triangle, we can just use Pythagoras. So we have c squared equals a squared plus b squared. Rearrange and substitute values in, so c is equal to the square root of 34.6 squared plus 20 squared, which brings us to 39.96 meters. Now we're on an inclined plane, so from our dynamics unit, we know our force normal is going to be equal to our force perpendicular. And our force perpendicular we could get by doing mg cos of theta. So our force of gravity times cos of our angle. Now I've partially filled out this equation. I haven't bothered putting my m in because I'm hoping later on when I do my bigger equation that all my m's cancel out. If not, I will substitute my value in later. So I've got my force normal equals m times 9.81 times cos 30. Which, if we simplify that bit, becomes m times 8.5. So that's going to make our force of friction, our coefficient times m times 8.5. Our coefficient of friction was 0.15. And we'll multiply that by our 8.5, still leaving that m there. So we've got force of friction is equal to m times 1.27. Okay, so we're going to continue on. So we have our equation. We've got 1/2 mv squared minus v naught squared plus mg change in y plus force of friction times distance equals 0. So we'll start filling in some of the information we have. On the previous page, we came up with our force of friction, so we'll substitute that in. Now, we can also see that each term has m in it. So we've got our m after for 1/2 in our kinetic energy formula. We've got m at the beginning of our gravitational potential formula and m at the beginning of our thermal energy formula. So all those can cancel out. We can also get rid of our v naught squared term because the box is starting stationary. So v squared minus 0 squared would just be v squared. At this point, we want to gradually start rearranging to get v squared on its own. So I'd move the other two terms to the other side. We then want to get rid of a 1/2 in front of a v squared, so I'd multiply every term by 2. And then take the square root of both sides. Substitute in our remaining values that we haven't put in yet. And we should get that we have a velocity of 17 meters per second. Okay, next example. This one, we have an inclined plane. We have a box that's starting moving upwards at 10 meters per second. The box weighs 3 kilograms. And we want to know what coefficient of friction would be necessary for a box to stop at a height of 2 meters. And we want to do the question to 2 significant figures. Okay, so first thing I'm going to do is figure out what distance along the incline our box moves. Now we know it's going to stop at a height of 2 meters. So that would be our side of our triangle opposite our 30 degrees. So we have our opposite side. We want to figure out our hypotenuse. So we'd use sine, which sine is our opposite over hypotenuse. Rearranging that equation, we get our hypotenuse is equal to opposite over sine of our angle. So we have 2 divided by sine 30, which gives us a hypotenuse of 4 meters. We then have our equation 1/2 m v squared minus v naught squared plus mg change in y plus force of friction times distance. So I'll start filling in my equation for my force of friction. So we have essentially the same equation, except for I've put in mu mg cos theta for my force of friction, because we know our force of friction is our coefficient of friction times our force normal, which we know our force normal is our force perpendicular, which is mg cos theta. Okay, so we'll continue on from this formula from the previous page. Okay, so one thing is we can get rid of our v squared because we know our final velocity is going to be 0. We can also cancel out our m from every term. So that gives us 1/2 times negative of v naught squared plus g change in y plus mu g cos theta times our distance. So my next step would be to move what remains of our potential energy and kinetic energy to the other side of the equation. So that gives us mu g cos theta times d equals 1/2 v naught squared minus g change in y. Now to get our coefficient of friction on its own, I will divide both sides of the equation by g cos theta times d. So we've got our coefficient of friction is equal to 1/2 v naught squared minus minus g change in y over dg cos theta. Substitute our values in, and we get coefficient of friction of 0.89. Okay, so on to practice, there should be some questions on page 166 of your textbook. There is also a practice worksheet I'll hand out.